All right, so today we're gonna finish the lecture about inheritance. It's been 6 lectures. I think we talk about quite thoroughly about inheritance. I think for your programming test, the last one, next Wednesday. So that one there, it's gonna be based on lab number 2 and number 4. Definitely revisit quickly just about how exceptions should be implemented and how arrays should be manipulated as well. And lab 4 is definitely more relevant, for sure, about inheritance. And you already have seen the guide and also example questions. You can definitely give it a try. Give yourself some timer, time yourself, and see how much you can achieve. Maybe within 1 hour or 18 minutes, something like that. All right. And then after today's lecture, we're going to start talking about recursion from next Tuesday. So I will also point out to you some study resources. Everything has been on the lecture side. There might be a link I need to fix very quickly after class, but I'll fix it. But you definitely got all the resources you will need about studying for recursion. All right, I'll talk about it. Maybe after we still got a small number of examples to go through. And also we got to talk about polymorphic collection today. That's really what we have been studying inheritance for. It's really the powerful concept that we're going to see. Okay, we'll see examples. Any questions about the course? I'm expecting to hear back from the TA about your programming test 2 grading, maybe late afternoon Friday. So I'll try to definitely process that quickly over the weekend, and then I will reach out to you about the result and feedback, hopefully Sunday early evening. If not, definitely Monday early morning. So you can definitely hear back the result about programming test 2. And for your written test number 2 yesterday, because there's one question that will require the grading by TA, I also try to make it quick. So tentatively, let's say by next Friday, you can hear back from me about written test number 2, right? Of course, after that, you can also speak to me if you got any concern, always, all right? Any questions about the course? All right, so if I were you, I would definitely slowly and steadily start going over all the materials that have been covered so far in the course, because your exam will be cumulative. It's definitely gonna be a big component, right? We kind of know that since day 1. If you want any tips about how to study for the exam, speak to me after class or during office hour. I can definitely give you some ideas. Okay. All right, let's do a quick recap, and then we'll finish off some topics for inheritance. Not difficult, but fundamental. Okay. So last time, we introduced this idea about instance of operator. I would say when you study this operator here for the exam, you definitely want to think about instance of is really a way for you to do a safety check before you do some subsequent typecast. So whenever I say X instance of Y, I'm basically asking, is it safe for me to cast X to Y? That's essentially what I'm asking. Or you can think about intuitively, can X dynamically, or its dynamic type, fulfill the expectation of Y? Right here, right? We talk all sorts of details on Tuesday, so you want to review to make sure, number 1, when does this instance of expression compile? It will compile if the corresponding cast from X to Y compile, okay, number 1. Number 2, when will this particular expression here at the runtime return true? You can think about this will return true if this particular typecast is not going to run into class cast exception. Right? On the other hand, if this one here returns false, that means this corresponding cast will have the risk of having class cast exception, in which case you should really use the if condition to check the instance of and avoid getting there. Right? That's kind of the logic you want to have, want to think about. And I think you guys asked some very nice questions last time that kind of triggered me, to do this table together. I should also mention this table to your fellow student in section B. I think this one here quite nicely summarizes about the connection between these two, instance of and also typecast, right? Look at this table here and make sure it's really well understood before you write the exam. Since there's no data sheets that's allowed in the exam, so you have to somehow understand all the concept, right? I wouldn't say memorizing per se. There's going to be some memorization, of course, but at the same time, always remember the intuition. So you will be able to derive many things if you have to. Right? This table here, I can say, definitely summarizes what we spoke about on Tuesday. Right? And the generalization about different classes, what kind of class is going to give you compilation error for instance of, what kind of classes is going to give you, let's say, true or false at the runtime for instance of, right? That's also something we said about. You can also check the recording or reach out to me later. And we did example here. So if you do instance of check, if this instance of return true, that means it is safe for us to do it without worrying about class cast exception. On the other hand, if this instance of returns false, that means we should really bypass because we will run into class cast exception at the runtime. So that's a very good safety check, always to do. Okay, some exercise you can try. And also we talk about, get class versus instance of. So I would say in the programming test, let's say for next Wednesday, most likely you will have to use instance of. I think it will be just much easier because if you have to do any typecast, maybe this will be something to do first. Or you want to check if the object you're retrieving from an array is dynamically some class. I think instance of will be the best one to do. We'll see examples today, actually. Talk about polymorphic array very soon. And then instance of, just more example here, and also about the static type for the context objects. And then we revisited the call by value idea over here, right? So whenever you have a method call, if you recall, we got this method call here. And this method is declared right here in the callee side over here. Parameter and also arguments, they have statically maybe different types, T1 and T2. Implicitly, there is a variable assignment, as we learned earlier. It's going to be the parameter assign the arguments. Right? As soon as we have variable assignments, we have to recall the rule of substitution. Because in general, T1 and T2 over here might be classes in some inheritance hierarchy, in which case you got to be careful. Okay? So the rule will be the T2 over here for the arguments statically should be a descendant of the static type for param, which is T1. Okay? Just remember that kind of intuition. All right? And then, yeah, again. So static type for arguments should be a descendant class of the parameter, in this case, resident students. And we spoke about if you, so let me show you here. If you actually make this method here, the parameter type somehow very high in the inheritance hierarchy. You can see the student here is right at the top, right? If you recall, student here is right at the top. What are the descendants classes for these students? Basically everything. So in that way, whenever you want to call the addStudents method, you will be able to pass any arguments whose static type is a descendant of students. So that will give you many options. So that's exactly how we can create polymorphic array at the runtime. That's something we'll see, right? That will be the second example we'll do today. Okay, just keep that in mind. Right, just make sure you will know how to judge to see whether things will compile or not compile, right? By using the rule. Always remember the call by value, where you just go from there. Okay. Any question for last time? All good? Okay. Okay. So let's now start with one example. That one there is something you haven't really seen per se, but it's really built on what we understand about typecast and also call by value. I think that'll be a nice example just to warm up, right? So that might be the last one that we're going to talk about, like a class cast exception. So let's take this one. It's a review exercise, okay? This one here corresponds to slide number 79. I believe there are 4 slides in total about this example, but I'll put them all in one go, just one page, just to see how they can be compared and contrast together, right? Okay, I'll guide you through. Let's say we are considering this addRs method, where the parameter rs statically is resident student. Okay, we'll focus just on this method here. And then let's say we got 1, 2, 3, and 4. 4 fragments of code. Each one of them is going to call addRs, 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 and addRs. Okay, we're calling the same method. So first of all the initial method call would not compile. Let's start with that and see why. I'll take one for example. If you just look at, let's say, the first one here, okay, I'll make it a little bit larger. Okay, right here. Right here. You can see this method call here. Call by value, we got s, the arguments, rs, the parameter, right? Let's now just make this one very explicit, okay? Just this one here. So think about we got s over here, and the method we are calling is rs, okay? If we are trying to connect them using call by value, we got RS is assigned S. And this is not going to compile because static type for S is students. Can student fulfill the static type for RS, which is resident students? No, it cannot, right? Obviously, right? Hopefully that's something you're already pretty proficient, okay? So this is not going to compile, okay? Okay. And you can judge in a similar way because student here, S. Student here, passing S. And similarly, this one here, NRS, non-resident student, NRS. Also, non-resident student cannot fulfill resident students as well for the similar reason. Okay, so all these lines are not going to compile in the beginning. So now, whenever you want to pass an argument, but somehow the static type is not really compatible, you may try to work around just at the compilation level, just to do some cast. Okay? But if you recall the exercise we did right before written test number 2, we can cast basically from one type to another type, just by doing some upward cast and then downward cast, right? You can cast all the way up to objects and then downcast to that particular type. You can always somehow work around with a compiler. But of course, you gotta watch out. You may still have to pay the price for a class cast exception at the runtime. Let's see. This is the example we want to do right now. So what I want to introduce is, let's say we got this line instead, okay? We're still having S like before, right? Or NRS. But let's worry about this one here a little bit later. Let's do that in isolation. Let's look at only these three. They're more similar. Okay. So what I want to do is I want to somehow do a cast right here. All right. Let's talk about this cast. Let's do a final review just about typecast, right? If I look at this cast over here, okay, we'll put a star. Okay. This cast over here. Number one, the cast compiles, because the static type for S is students, downcasting to resident students, right? That's something you know, so I wouldn't bother you too much. So the cast compiles because it's a downward cast. Downward cast, okay? And then number two, if the cast compile, we will know that the whole expression for the cast is going to have the static type corresponding to the cast type, which is resident students. Okay? So consequently, the cast expression has the static type corresponding to the cast type, which is resident students. So now, if we pass this whole thing, the cast expression, as the method arguments, in that way, resident students can it fulfill resident students? Yes, can, right? So you'll be as if, thinking this way, okay? You can think about this whole thing here. This is the argument we are passing right here. Oh, let me do a little bit better. Think about this is the argument we are passing. And this is the parameter, right? And then when we try to connect them together, again, we got call by value. Call by value will be as if we say RS assign cast RS and then S. And you can, of course, can check that this will compile. All right? Follow so far? Okay. We're basically just saying rather than passing just S as an argument, which we know wouldn't compile, we somehow downcast S into resident students. The whole cast expression is going to compile, which has a static type resident students. At least we can make the compiler happy, right? That's what we want to do. So you want to think about what we are going to do is think about this is some fixed line, okay? This is some fixed line. And we're going to replace this one here by the fixed line. Also, we're going to replace this line here by the fixed line. Also, replace this line here by the fixed line, right? The same, right? They're all going to compile because all the S over here has the same static type. We're just doing the same downcast. Okay, so compilation, discussion is done. Compile. And then runtime. Is every one of them going to be class cast exception free? That's the question. In which case, we will have to look at dynamic type. We're going to look at student here, non-resident student here, and also resident student here, right? So that's a dynamic type, all right? So quick question for you guys, right? Given that I change all the three method call to be this line, which we just explained, it's going to compile. Which one or which ones are going to have class cast exception? At least one. How about that? Okay, everyone except for the last one. Would you agree? Would you like to say just for the first one, why would you have a class cast exception? Just for the first one, which is here. For it to be class cast exception free. It already compiles, right? Oh, yeah. Yeah, good. Okay. No, it's okay. Very good. Spot on. I'll write it down. So this one here is going to give us, yes, class cast exception. Because dynamic type is students. Dynamic type students is not descendants of the cast type, which is resident students. Okay, obviously. And the second one, similar. Can non-resident students fulfill resident students? Nope, it cannot, because non-resident student is not a descendant of resident students. Also, yes, class cast exception, because dynamic type non-resident students cannot fulfill the expectation of the cast type, again, resident students. Okay, I just try to change the way I'm kind of phrasing it, but both are acceptable, just in case you have to write the explanation. All right, the third one here is not going to be, it's actually going to be class cast exception free, because dynamically resident students, of course, can fulfill itself. Right? So this one here will be no, class cast exception free, because dynamic type resident students can fulfill the cast type resident students. All right. Can you see the flow here for the example? We kind of started with something like a method call that wouldn't compile, and then we try to cast the argument before we pass it for the method call. And then we try to argue about compilation for the method call, and then if the class cast is going to write into any exception at the runtime. That's what we're doing. Okay. All right, the final one. Guys, question. Initially, NRS, which is statically non-resident student, which cannot fulfill, let me say it again. NRS over here, statically non-resident students, which cannot fulfill parameter resident student, right? Okay, so now, if I try to cast over here to resident students, am I going to run into class cast exception? Let's say that's an exam question, right? The question goes like this. Let me say it one more time. Let's say this is an exam question. How would you respond? Given that this one does not compile, I want to go with the following fix. I will cast NRS to resident students so that the cast type is going to fulfill the parameter type resident students. Okay, you're saying that it seems like the typecast is not even going to compile. Okay, anyone else agree? Okay, good. So this one here is not even about, we're not even reaching the runtime stage really, all right? So this cast over here is not even going to compile. So always be careful to see what checks you have to do, right? So this one here is neither upward nor downward cast. So does not compile. Compile should be cross, all right? Because NRS statically non-resident students. When you want to cast that into resident student, cannot do it. Okay. Also, I also write down something for you as well. If I write another expression, if I say NRS instance of resident students, let's say if I write something like this, okay, I say NRS can its dynamic type fulfill resident students. Is it going to be true or false? False, okay. True or false? False? Anybody else? Should it even compile? Right, okay, remember, okay, that's good. You know, I'm glad I kind of gave you guys this example here. You deserve that, okay? I think, okay, let's think about this one here. We said earlier, this will compile if casting NRS to resident student will compile. We already said this is not going to compile. So this will not compile. All right? Guys, be careful, okay? Okay. I'm a little bit partial to you guys. I didn't give this example yesterday, but I should really mention to your fellow students, right? Just be careful, okay? So this one here, I'll write it down, okay? Fail to compile. Because the casting from the NRS to RS failed to compile. Okay, be very careful about this. So I think watch out for this, especially for the exam. Okay. All right, any questions about this? All good? Okay. So let's now move on to something I would say arguably the most important part for the inheritance lecture. So we have done 79, 80, 81, and also 82, right? So all these are done, right? All the examples we just went through. But you know, it doesn't hurt to really go over the slides a bit just to see if there's any more information you can pick up. Let's now talk about slide number 83. But before that, I can see that at the bottom there, there's a little box there. I want to show you, and when you study for the exam, also try to go between these two slides. I'll show you, it's a hyperlink. If you go to the end of slide number 83, okay? So slide number 83, basically we are declaring student management system class where we got student array. But now, remember student is a class in some inheritance hierarchy, right? Okay. Now, if I click on this link here, that will take us back to slide number 11, all right? Slide number 11 is more like a design number 2 that we did earlier. Remember when we talk about different design before we talk about inheritance? So this is the design where the resident students and non-resident students have nothing to do with each other. There's no inheritance. So we have to have separate arrays and then separate counters and also separate loops. So that's really something that might work programmatically, but it's a bad design. All right? So when you study for the exam, compare and contrast without inheritance and with inheritance, how things should be done differently. All right? So this is something we already did, you know, earlier, a few weeks ago. So let's now go to 83 again. Okay? Let's now dive into this particular inheritance version in detail, and we'll introduce the idea called polymorphic array. Okay? And very likely you will have to program polymorphic array in your programming test next Wednesday. Well, that's something you did on in lab number 4, implicitly anyway. Okay? Let's talk about this one here. Okay. Let's start with just this class, right? Very simple. Okay. So let's remind ourselves. We got our student management system, and also we have our students array. So students right here. Let's remind us right away. I'll put it down. So student means the elements, each element at each index. Elements have the same static type, which is students. However, dynamically, we'll see, because of polymorphism, statically it's just students, which is at the top of the hierarchy. Dynamically, dynamic type for each element may be different. It could be students, could be resident students, or could be non-resident student. It can be any of its descendants. That's something we'll see. Okay? So we got array, we got counter, and then we are using this most accommodating version of the addition method. Okay? So let's now also remind ourselves very quickly. If you look at the student here, call by value and rule of substitution tell us any arguments whose static type is a descendant class of students here can be passed. Okay? Any arguments with static type a descendants of students can be passed. Consequently, at the runtime, we may have different dynamic types, either resident students or non-resident student. That's what we'll see. But before we get there, I just want to give you some look ahead. Okay? And the definition for this method here, very standard, right? I don't need to bother you with that. I'm pretty sure you know how to do it. And we look at this one method here called register all. Okay? That one there is going to invoke the register method here. Okay? If you look at this method call, right? I think one of your practice test question for written test 2 is about whether or not a method call will compile. How do you judge? You have to look at the static type of the context objects. If the static type of the context objects can have that particular expectation, then yes, it will compile. How about in this case? Okay? So let's say here, if you just look at students at index I, that one there, as we know, every element in the students array statically is a students, right? So we know that the static type is a students. And then we try to look at the register method. Is register method an expectation for students? Let's go back to the student class. And then we'll see that in the student class, we do have the register method right there. So that's why it compiles. All right? So you can think about this register here is part of the expectation. Okay, it's a part of. Okay, let me just not get too complicated. It is part of the expectation of the students. So this can be called. And let's say a little bit more. Okay, and then we'll trace the code. Apparently, we are trying to go over the students array, element by element. Polymorphism kind of tells us statically is a student, yes. Dynamically, it could be resident students or non-resident students, as we'll see. Okay? The index over here, I, we'll see the array we're going to build is going to be, I'll show you how it can be built, but I'm going to have just two indices, 0 and 1. Okay? I'll give you some look ahead quickly. So that one there is going to be I here, maybe 0 or 1. And then we're going to trace to see what the dynamic type should be when we get to that particular index. Okay? Dynamic type of students array at index I. Okay? I'll leave this table just unfilled out, just for now. We can fill it out in a moment. Okay? Let's now look at this fragment of code and see how we can build the polymorphic array. It's pretty straightforward, so don't overthink, right? It's pretty straightforward. So what we'll do is, let's now try to, line number 1 to line number 5 is actually very easy to trace. So 1, 2, 3, 4, 5, right here. Okay, let's take a quick look. So what we have is we got RS, we got NRS. We got RS, we got NRS. RS, dynamically, resident students. Resident students. NRS, dynamically, non-resident students, non-resident students. And we can set a premium rate and discount rate accordingly. Premium rate and discount rate, right? So far, so good. And we also got a student management system, which will get an array of certain size. Initially, all the slots are simply just null, right? That's something we have been doing for all your practice tests and also the labs. So line number 1 to 5 should be quite nothing new. Let's now look at 6 and 7. This is where we're going to build the polymorphic array. All right? So I'm going to say, let's say for line number 6, right here. Okay? But for this method call, let's try to check to see whether or not it's going to compile. Okay, very quickly. Let me hand wave a little bit. RS has the static type resident students. Can resident student fulfill the parameter type students? Yes, he can, right? Similarly, can NRS right here, statically non-resident student, fulfill students? Yes. So both method call compile. Make sure you can do that, right? So both of these are going to compile. Let's execute them. When I do line number 6, that one there is going to let index 0 point to wherever RS is pointing to. All right. So that one there, let me just do this one here. Okay, like that. Okay, so that would be at index 0. And the next line, when I do sms.addStudentNRS, so that means next index, which will be index 1, is going to point to wherever NRS is pointing to. So like this. All right. So that one there is going to be right here. I can do better. So right here. Okay, so far so good. So now we have got a polymorphic array. How? Statically, index 0, index 1 of this array is students. Right? That's what we declare them to be. Dynamically, index 0 points to an object dynamically is the resident students. Index 1 dynamically is a non-resident students. Both are valid because resident students is a descendant of the static type students. Also, non-resident students is also a descendant class of students. Right? That's polymorphic array. Okay. So I can write it down just to summarize. And then we'll do some little bit tracing. So polymorphic collection. So of course, in this course, we just talk about array. That's kind of the only collection that we kind of talk about. We don't talk about array list or hash table, set, array list, etc. But idea will be very similar. But let's, whenever your collection actually store multiple objects, then very likely they can be polymorphic. Okay? So you can think about this one here. Static type of elements. For example, simply just students. And then dynamic types of elements. They will simply just be descendants. Descendants of the static type. Right? Resident students or non-resident students. Right. Question so far? Okay. I hope it's still easy to follow. Okay. Okay, next line. We create a course called EECS2030 right here. And now we just want to call this method here, register all. Okay, just one thing to note. Get tuition will be a little bit more interesting when we get there to trace. If you look at the dynamic binding, the register method is declared already in the students, but none of the child classes ever try to override it. But that's okay. You don't really have to override every method you actually got inherited. So you can think about the register method here has only one version. That version is more like a default version of the equals method that's being inherited, right, to every class. So this is inherited to this one here and also this one here. So whenever you're trying to call the register method on any resident students or non-resident student objects, you will just call the same version that's inherited because none of them has chosen to override the register method. Okay? But get tuition is another story, of course. We'll get there. Okay, let's just trace this one very, very quickly. Okay? And I'll just point to you the essence about what you should really watch out for. So this one here, I want to register all the students. So register all. We already did some preview over here, right? Because at the moment, the counter is simply 2. Okay? So I value is going to be 0 and 1. So let's do a little bit of quick tracing. Iteration number 1. I value is going to be 0. In which case, we are looking at this particular object right here. All right? So you can see I kind of put some expression here aside. I'll show to you. You can see SMS.ss. Oh, sorry. I think I can do this one instead. This one, okay? So here you can see SMS, the student management system objects, go to the array, and then I go to index 0, right? So that's what this expression is about. So this is for iteration number 1. Iteration number 1, when I is equal to 0, right? You can see now the dynamic type that we are having is resident students. Resident students. Quick check, okay? If I try this expression here, say instance of different classes over here, what value should I get? For your information, all of them compile, but you can, I will leave that as an exercise for you to judge why they compile, right? So what will be your answer?
Instance of?
Instance of, yeah. Tell me the result for all 3 of them.
Okay, for S of 0, which in this case is RS,
Mm-hmm.
resident students, so only resident student will be true, and student will be true.
Mm-hmm. Okay, that's pretty good. So this expression here, it refers to this particular object from index 0, dynamically resident students. Can resident student fulfill non-resident students? No, not the descendants. But it can fulfill both itself and also students, right? So false, true, true. So it will be false, and then true, true. Guys, are you okay? Am I going too fast for the instance of check? You okay with that? Okay, please do slow me down, because most likely we can finish earlier today. We don't have that much to cover. Okay, so yeah, go ahead.
Go over why the first one compiled.
You mean why the first one will compile?
Yeah.
Okay, sure. It's a fair question. Huh? Yeah, indeed, indeed. Yeah, very good. I think your fellow student actually already answered, but I'll just repeat. Okay, if you look at this line here, there's a compile. So you want to think about instead. I'll put it here. If you try to cast SMS.ss at index 0, oh, this might be something you haven't seen before, but it's definitely valid, okay? If I try to cast that one to non-resident students, we're asking, can this cast compile? If that cast compile, the instance of compile. Let's see. So statically, as your fellow student said, SMS SS0 is students. Students to NRS is downward cast. You will compile. Yes. Yeah. You can do similar argument later for others. Compiles. All right, good. And then, of course, for that one there, for the first iteration, we're going to call register, and we're just going to call the register from student. There's only one version, right? So we call that one. And for iteration number 2, it's going to be I being 1. So now 1 will be the index here, and you're going to go to a different objects. It's a different dynamic type, happen to be just a setup, right? So it's a non-resident students, all right? So that one there is a non-resident students. And let's do a similar exercise. If I do that over here, right, you can see now it's index 1 right here. Okay, yeah.
Now non-resident is the true and resident is the false.
Yeah, just one moment. So that'll be iteration number 2 when I is equal to 1. So now we know that non-resident students here is dynamic type. Can it fulfill itself? Yes, it can. Can it fulfill resident students? It cannot. Can it fulfill students? Yes. All right. So it's going to be true, and then false, and then true. Of course, when you compare, you will see that between the two, you can see this is the one that's false, and this is the one that's false, which makes sense because dynamic type is different, right? Also because index is also different. Polymorphic array simply tells you that it's possible for you just to simply have a variety of dynamic types. Of course, it might just happen that you just put resident students only into the polymorphic array. That's also possible, right? Just saying you got the flexibility, okay? All right, let's do a final one, and then we can take a short break, okay? This loop here is doing something very similar, right? We still got I from 0 all the way to 2, right? And then we're calling get tuition, okay? Very similar idea, okay? So here, I just want to do a little bit of annotation for you, so it'll be easier for you to study later, okay? So if you look at this expression here, right? Similar expression as we did earlier. So I can be 0 or 1. Dynamic type accordingly is going to be resident students and also non-resident student, right? So now, let's do a little bit of efficient tracing. When I is equal to 0, when we call this dot get tuition, it's going to call the resident students version using premium rates. In the second iteration, when I gets incremented to 1, this expression here, dot get tuition, is going to call non-resident student version using discount rate. Guys, follow? Question?
Is get tuition implemented in student class or no?
Yeah, it does. Yeah, maybe it's been a while. Okay, let me remind you guys very quickly. So students has the get tuition, yes, it's there. And if you recall, that one, they only calculate the base amount, just add up the fees of the course. And then both of these two classes override that method, okay? The way resident student override it is by get tuition, like a base amount multiplied by premium rates. And this one is the super dot get tuition multiply discount rate. That's what we did earlier, right? Good. Okay. Yeah, let me just recap very quickly. For this loop here, number one, figure out how many iterations we got. So we got 2 iterations. And then for every iteration, you're looking at the different objects at different indices, in which case you can trace to see what's the dynamic type. In this case, they're different, resident student, non-resident students. So this expression here, when I is equal to 0, the get tuition is going to call the version from resident students. When I is equal to 1, get tuition is going to call non-resident student version. That's really the spirit for dynamic binding. Okay? Okay. Guys, any questions? All good? Okay. Why don't we take a very short break, and then I still got maybe about 2 or 3 more examples, and then we're done for inheritance. Okay? Yeah, take a break. And I didn't take attendance for your section B fellow student yesterday because of the test, so let's not take attendance today. Okay? Just take a break. Okay, so we try to see how you can build a polymorphic array before the break. Let's, for now, assume we have got this array already, right? We got index 0, index 1 with different dynamic type. Okay, we're going to reuse this structure. I want to talk about one more thing. Rather than having the method parameters being polymorphic, let's talk about the method return type being polymorphic, right? It's also very easy to adapt to. Okay, I'll show to you. So we are done with, let me just show to you on the slides. So this is something we just went over before the break. And then visualization. Oh, there's something I forgot to mention. So in the iPad notes, when I went over the example with you in the class, in the interest of time, I didn't really try to trace from scratch. You may actually want to practice yourself to really trace the code over here line by line and see if you're able to visualize what's going on. This might be the kind of stuff you might be given, in the exam. So you want to know how to trace them. Okay, give it a try. Okay, of course the solution is just whatever we presented, right? All right, I'll leave that to you. And then let's now talk about return type, okay? So now it's slide number 86 I'm talking about. We're getting to the end very soon, okay? Let's talk about one more, okay, here. This one will be quick. Let's now look at the same student management system class. Again, we still have our student array, okay? And we have our add students, parameter students, very accommodating, right? As before. Let's now add one new method here, accessor. Get students. Get student is going to take some input parameter, just I. I itself is meant to be used as an index into the SS array. So we just check in to see if the index is not valid, for example, if that's negative or maybe too large. In that case, we just throw. There's something called illegal argument exception. But if you want to create your own exception, that's also fine, right? So just saying we're going to pass the valid index. Once you pass the valid index, you somehow want to return using the index and return the corresponding objects stored at that particular index in the student's array. For example, if I happen to be 0, I want to return this object. If I happen to be 1, I want to return this object, right? Simple method, right? Just to illustrate, okay? How do we make this happen? Sorry. The way to make this happen is we make the return type of the method students over here, all right? So now let's do some quick arguments right here. So some intuition. The student here, okay, let's now write some notes down. The student here is the static type of the return value, okay? Static type of return value. And consequently, we know that dynamic type for the return value can be what? Descendant classes of students, right? Polymorphism everywhere. So this would mean dynamic types of return value are descendants of students. All right, so that's very important stuff you want to kind of tell yourself right away whenever you see any return type like that, especially if the return type is a class in some inheritance hierarchy. All right. And the way we program this method here, just to make it more explicit for you, we declare some local variable called students, so-called S, right here, right? So I deliberately choose the static type for this return, like a local variable, just the same as a return type, just to show you how it can be polymorphic, right? Just choose the same. And then eventually we want to return this variable, okay? Eventually. And the way to really get S assigned, because initially that's simply just null. You can see this variable assignments. Right? Let's now make it a little bit bigger. Okay, let's do the analysis very quickly. This line here, compile, because let's look at that. SSI, students. S declared to be students. Can students fulfill students? Yes, compiles, not a problem. Okay. And we know that SS over here is a polymorphic array, which we just learned before the break. All right? This is a polymorphic array. Specifically, when we look at different indices, when I is equal to 0 and 1, dynamic types will just be different. So we assume the same structure from before. Resident students, non-resident students. Okay, let's put it down quickly. So it's going to be resident students versus non-resident students. Okay, so we know that when we return something from this method here, dynamically it could be resident students or it could be non-resident students, depending on which I you pass. Let's now test this quickly. Okay. Let's now look at the first few lines. Very simple. You can think about all these lines are just to set up what we had before the break, right? So this whole structure, polymorphic array, right? You can trace it, very simple. Just create the various objects. And now you want to look at two lines, okay? I'm going to highlight them. Line number 1, we got this one here, okay? Line number 2, we got this one here. Okay. Let's now figure out number 1. Why do these two lines compile? Let's say this one might be quite easy for you to see. How do I judge to see this variable assignment will compile? How do I judge? How do you know the right-hand side static type is the students? How do you know? The method return type over here is the students, right? Okay, good. Make sense? Okay. So you can think about statically get students and also statically get students. So the static type is students. And here, the static type is also students. Okay, simply because we got students as a return type. It's the static type for any return value. But dynamically, it might be different. Okay, so now for the first line, when we say S is assigned over here. So what's going to happen here? For this method call, let's trace that a little bit. For this line here, we have the index, we have to give the I value 0. If I is 0, that means we got 0 over here. So we got 0. So that's going to give us basically this object right here. So that means after this, S is going to point to this particular objects, right? So that means the S over here will have dynamic type, resident students. After that, of course, you can do the instance of check, which we did before the break. You can do it again as exercise for yourself, right? And when I say S.getTuition over here, S dynamically is the resident students. It's going to call the resident students version, dynamic binding, okay? And then when we get to the second line, the second method call, calling the same method, but it's a different input value. So now if I say input value 1, okay, if I go to this method again, I is not going to be 1, meaning that I'm going to get access to index 1. I know that index 1 has a dynamic type, non-resident students, right? That would mean after this variable assignment over here, S, rather than pointing to here, it is going to point to wherever index 1 is pointing to, right here. And that one there has the dynamic type non-resident students. Okay? So that one there has a dynamic type non-resident students. So when I do S.getTuition, it's now going to call a different version because now the dynamic type for S has been changed to non-resident students using discount rate. All right? Any questions? So the main message to get from this example here goes like this. By calling just the same method, get students and get students, by passing different input argument over here, you might just get dynamically the return type of different dynamic type. It could be resident students when you get index 0, which is here. Or it can be non-resident students when you get index 1, which will give you this object. Right? So that's really the essence for studying this example here. And one more thing, look at this line. Is this line going to compile? Just this line, last line. Because here, okay, so before you answer, okay, so index 1, I know that it's going to point to some non-resident student objects. So I want to use a non-resident student to store that. That's my intention. All right? Is this going to compile? Why? Yeah. Give it a try, yeah.
Oh, because we're returning a static type student.
Ah, exactly, spot on. Yeah, now you got the essence, right? Good. Okay, yeah, I know you said the same thing. Yeah. All right. Very good. So this one we know, as we learned earlier, this one here, doesn't matter the actual value here, static type is students. Oh, sorry, I can write a little bit better. Which is not a descendant class of non-resident students. So it's not going to compile. All right, so watch out, okay? Very good. All right, so that's just pretty much the final example for inheritance, but I still got a few housekeeping stuff I want to mention them quickly, okay? And then we're done with inheritance. And then I want to point out just a few study resources for you about recursion, and then we are done for today. Just bear with me so we can finish earlier today, okay? All right, so you will see that at the end of the inheritance lecture, I gave you a table like this, right? It might seem a little bit daunting at first, but it's a very, very precise way to summarize what we have learned in the entire inheritance lecture series. Okay, I'll give you one example. I'll choose the easiest one. How about that? And then if you really go over them, I will encourage you to do so. Okay, so this is saying, whenever you got any variable assignments, for example, x and y, they could be arbitrary type. In order for this one to compile, what's the requirements? Well, right-hand side, static type, must be a descendant class of left-hand side static type. Exactly what we said. So these are the rules that Java compiler in Eclipse actually implements. That's exactly the rule they got to follow, right? These rules, you don't really memorize them per se, but I think about how the intuition we have been discussing in the inheritance lecture can help you understand why they are being checked, all right? So try to look at every one of them and really try to make sense out of them. Okay, I'll leave them to you. If you got any trouble understanding some of them, reach out to me. We can definitely go over, but you have to do them first, all right? So that's a table. And final example, okay? And I think this one was also briefly mentioned by Tian Tian on Tuesday when she did the review session, but we can review this again. I can tell you the lesson first. Whenever you're calling some method that may have multiple versions, which overridden version should you choose? The answer is you want to find the closest ancestor. All right? Just remember that. Closest ancestor, okay? Including yourself, of course. Yourself is also an ancestor, okay? The setup is the same. So let's say we got three classes. We got A, B, and C, okay? A, B, and C. And let's say in this case, none of these three classes has overridden the equals method. So there's only one version, default version right here, okay? And then we have setup. So we got C1, dynamically is type C. So C1 is now the context objects. So now we know that we should really call the C version of the equals. So now there is no explicitly defined C. So go up. B, nothing here. So go up again. Nothing here. That's already the top of our hierarchy. But implicitly, object is the ancestor or parents of every class. Again, you go up. So you're going to call this version. Okay? So this version will be called just object version. Okay, make sense? Okay. Second scenario. Same setup. So we still got C, and then we got C1. So we should call C1 version. But in this case, C itself already got some overridden version. C is its own ancestor. That's the closest one. So take this version. You don't need to go up any further. All right? So C version. You can think about this is already the closest ancestor. Just C itself. All right, next one. Say this one here. Again, we got dynamic type C and also C1. C does not have it. Go to its parents. Then you got B. And B has it. That's the closest one. Right? Do we have to go any further to objects? We don't have to. As soon as we have found one, that's the closest. Right? Because you go bottom up, it's guaranteed. The first one you find is going to be the closest one. So it's going to be B version. All right. Guys, any questions? Now we're completely done with the inheritance, okay? So I would definitely highly encourage you, maybe starting from the coming weekend. I know you have to get busy preparing for your programming test 3, but definitely start going over all the materials. iPad notes, written notes, slides about inheritance. It's definitely a big topic for the exam, that's for sure, okay? So bear with me for another few minutes, and then I'll let you go. Okay, I want to talk about something very quickly, so you can also start navigating your way about the study resources for recursion. Okay. For the inheritance slides, I think we're done with everything. So there is some suggested exercise you can give a try. Slide 89, just again a reminder about when should you consider static type and when should you consider dynamic type. Right? You can take a look. Same as what we said earlier. And the table I kind of mentioned earlier. And also just about equals method call. Okay, that's something we just did. And then, okay, you can definitely give a try on maybe some, take a look at this, this example here. Okay, take a look. Okay. All right, any questions about inheritance in general? Anything you want me to address? All good? Okay, give me a few minutes. I want to point out to you about the resources. So recursion, we're going to have 3 classes to cover recursion, which I think will be sufficient. My plan is just to give you some basics, and also I don't assume any prior knowledge about your recursion. So if you haven't learned recursion before, don't panic. Just make sure you follow through the lecture material, make sure you gain the understanding, and navigate through the study resources I gave to you. That should be enough for exam. Specifically, it will be also enough if you're going to take the 2101 next semester for data structure. They're going to definitely require recursion knowledge, but it'll be a different kind of pattern for recursion. But you're going to need some solid foundation from this course, which I'm going to give to you in the next 3 classes. Okay, I'll show you quickly about the resources, and then we're done. Okay, a few minutes. If you go over the lecture site, it's already there. So we got, okay, so this section here, we got recursion slides. Okay, we got a series of examples over there. We're going to start going over them. Okay, next Tuesday, Thursday, and also the final class on Tuesday, the week after. Okay, so there is one note right here. Okay, this note here basically is trying to summarize about all the examples that we're going to discuss about recursion in class. And the way I'm going to talk about recursion is, doesn't matter how hard the problem might be, there is certain general pattern you can follow to really program in recursion. You have to have base cases. You must have recursive cases. I'll talk about them, don't worry, next time. You may actually, well, it wouldn't hurt if you can go back to your previous math lecture notes. You may have heard about something or learned about something called mathematical induction. You can find some analogy there. So whenever you want to prove something using mathematical induction, you have to, first of all, prove about base cases. And then you have to state your inductive hypothesis, and you have to conduct some inductive step. The way we do recursion is very similar. All right? So you can, if you can, just review very quickly about mathematical induction you learned previously. That can help. But anyway, this notes. Just summarize everything we'll be learning. And then here, exercises. Right? So there are many extra exercises you can do. Number 1, so this is a past lab about recursion. I would say if you can just try to do that one there, anything I'm going to give to you in the actual exam is not going to be, it's going to be around the same level of this lab. Okay, take a look at that. And then there's a certain site called Coding Bat, right? Just one of the sites that's going to give you some extra practice, especially recursion 1. If you click on that, so they got many problems over here about recursion. All right, so start with that. For any one of them, it's more like an interview site kind of a style. You have the problem description, you have some input and output example, and then you can code up in Java, submit the solution online, and then it's going to behind the scene run some test cases and give you either green or red bar. Pretty much like our style, of grading your labs, sorry, not labs, the programming test. Okay, next. And then we got the codes. So I'm going to fix the link. Somehow the code is not really working, right? The link, I'll fix that, right? So all the source code I'm going to talk, all the source code for the example I'm going to talk about, it will be here. And if you want to see some tutorial session for recursion, I also got some previous tutorial, about 1 hour-ish, not very long. You can also take a look, the problems, source code, etc. Right? So all the study resources are already on the site about recursion. We're going to talk from scratch about recursion. I'll go very slowly in the very beginning when we talk about the basic example. And then we talk about how we can do recursion on the array. So there is one more advanced example called Tower of Hanoi. It's a fun math puzzle. You may have heard about it before in your math course. I think we should be able to get to a little bit of that. If not, I'll give you guys some assigned reading, some video to watch. Not very long, about 1 hour, just to study that example. All right? That'll be the plan. All right, thank you so much. Have a good weekend. I'll see you next Tuesday.